In the last video, we looked at the differences between a Lagrangian system of analysis and an Eulerian system of analysis. The Lagrangian system referred to tracking individual particles through time and space and figuring out the velocity, the flow description essentially by measuring the motion of those individual particles. Now, because those particles have a fixed they cover only certain trajectories in space, so we get information only in certain regions of space. So if I wanted to know what's going on over the entire system of interest, I would have to tag multiple particles and then measure all of them, and that's not very easy. So the alternative that we considered was the Eulerian system, where we essentially say, okay, here's my control volume, I'll measure what's going on inside this control volume. I don't know what the particle does before entering that control volume, and I don't know what it does after, but while it's in this control volume, this is the velocity that it has in all three directions. So that was fine, but then the problem is if I want to apply F equals ma, then I don't know how to apply that to a control volume as opposed to a particular particle, because in a control volume I observe over a time delta t, my set of particles inside that control volume might have changed during that time delta t. So there might have been some molecules or some fluid elements that left and some that came in, so I have a different mass in the system between t and t plus delta t. So question is, how do I apply F equals ma? And that's where the Reynolds transport theorem comes in. The Reynolds transport theorem essentially tells us how to switch between an Eulerian system and a Lagrangian system, and it uses the concept of control volume and control mass and conservation equations to achieve that. So we are all familiar with the control volume concept. It's something that you have seen in thermo. It's essentially a fixed volume in space independent of mass inside it. And so the contents of the control volume can change in time. And in principle, even the boundary might change with time. We are going to also introduce the concept of a control mass. This is the analog of the control volume, but now we are talking about specific masses. That means I have a specific set, I could even call this my system. This is a specific set of mass or particles which may have completely different trajectories, and so they may occupy different points in space with time. The approach that we are going to follow is to write conservation equations for a control volume and relate them back to properties of control mass. So if we were talking about a particular set of particles, we could always apply F equals ma because that's a fixed mass. The problem is that this fixed mass does not always occupy the control volume that we are looking at. So we need to figure out how to use the control volume to still get back to writing the equations in a way that it is applicable to the control mass. Let's do a brief review of intensive versus extensive properties, because that's what we are going to write conservation equations for in the control volume analysis. So you are familiar with this idea from thermo. There's this concept of mass dependent or mass independent properties. So intensive properties are independent of mass. Extensive properties are dependent on mass. And so things like capital H would refer to extensive quantities, small letters would refer to intensive properties, and so on. So I could say M, so if I had enthalpy, that would be H, capital H equals small h times the mass. E would be equal to the specific internal energy times the mass, giving us the total internal energy that's dependent on mass, and so on. So the Reynolds transport theorem essentially writes out an equation for intensive quantities. The intensive quantities that we will consider are the mass itself, essentially. So if this is the extensive quantity, the intensive quantity, corresponding intensive quantity would be 1, essentially, because 1 times mass gives us the actual mass of the system. Momentum of the system of the particles would be m, let me say mv. So the intensive quantity that corresponds to the actual system momentum would be just the velocity, and the kinetic energy of the system, which would be mv square by 2, would have a corresponding intensity quantity v square over 2.
You keep going, I have to step out real quick.
I'll be right back. So now I'm going to denote B, capital B, to be some particular extensive quantity, which could be the mass, the total energy, or the momentum of the system. So this would be for the system. That means this refers to the individual particles themselves. I could say that this equals the summation of the quantity for each individual particle, and this in turn I could write as each individual particle's mass times the intensive quantity small bi, and I could simplify this further as rho I delta Vi, right, where this delta Vi is the particle volume. And so essentially I could write that my system extensive quantity, if I were to replace this summation sign by an integral sign, I would say over the volume occupied by the control mass, it would just be rho B times dV. That's my system extensive property. What do we do with this? What we would like to do is we want something that says dB system over dt is something so this is in terms of system properties. In other words, this is a control mass property. What we want is something based on control volume. In other words, we want to deal with d by dt of integral rho b dv over the control volume and not over the control mass. And that's where Reynolds transport theorem comes in. RTT says you can switch from Cm to Cv in the following way. Derivative of the system property, which is based on the mass, control mass, that's equal to del by del T of rho b dV over the control volume plus a surface integral over the control surface That's the statement of the RTT, and this is intimidating, but it's actually not so hard to figure out. On the left hand side, we have an extensive property. It's an arbitrary extensive property of the system What we are saying is that this change of property of the system of those particles is equal to the rate of change of property in that control volume plus a net rate of leaving or entering of that property as a result of those particles leaving or entering the system. Rate of change of B due to particles leaving or entering. This is nothing but a restatement of Gauss's divergence theorem that you encountered in electrostatics. It's just written now for any extensive property. This is the statement. We'll figure out how to use it in practice in following sections. So, to sum up, you have looked at Eulerian system of analysis, you have looked at a Lagrangian system of analysis, and what we have now is a tool that lets you switch from one to the other, and the results that we get will give us an idea of how the velocity field varies in the Eulerian system, and now we can start writing conservation equations for the Eulerian system that will give us the field.